Hi students, welcome to Preliminary Chemistry and the water topic video number 10 on solubility and polarity. I just want to try and pull a couple of the ideas together here. This is really going to be a rehashing of some of what we've already looked at before, but it's just important that you know how to represent the reasons why different substances dissolve in water. And the main reason that we're looking at is that the polar nature of the water molecule is the key to its solubility. The fact that it is consists of two polar covalent bonds, and these two polar covalent bonds sum together to give us a polar molecule with distinct dipoles, a positive and a negative region, is what gives water its ability to be such an effective solvent. The bent nature of the molecule also allows us to have that symmetry about, or at least to find that there's a point where we can identify distinct regions of positive and negativeness within the molecule. And of course that means that we are able to create solutions on the basis of the fact that these water molecules can surround other molecules and separate them from the other substances that they may be attached to, or the other molecules, particles, atoms and ions and so on. So when we're looking at the like dissolves like rule, it's important that you remember that, but it's also important now that you can explain that, why that is the case, why substances will dissolve and why others will not. So the key to it then is that because we have a positive and a negative region in our water molecule, anything that is going to interact with that is going to dissolve in water. The simplest of these is an ionic substance. The next simplest is a small polar substance. Okay, covalent bonds with polarity within the bonds, which sum to give us an overall polar molecule, or at least some distinct regions within the molecule that can interact strongly with the water molecules. At the other end, we have nonpolar substances where there is only a temporary dipole, a little sort of negative and positive region, and you can get some interaction with the water molecules, but it's very weak and it's often insufficient to overcome the electrostatic attraction that exists between the molecules of the substance. And if that's not overcome, then there is no possibility for the water molecule to actually dissolve the substance. So these interactions are the electrostatic interactions that we've talked about, and they're just the rules about opposite charges attracting. That's all we're looking at here. We're just trying to see if there's any way we can find these oppositely charged interactions occurring between two different substances. So if you're going to try and model it, if you're going to try and draw it, then what you want to try and do is find places where there are opportunities for you to identify these distinct regions within a molecule. So I've oversimplified it here with just a little bit of smart art, but you can see that this particular molecule here, maybe if we go to a slightly different color for to contrast the blues, you can see that there's regions here of negative charge, and the molecules are orienting themselves in such a way that we get this electrostatic interaction between these oppositely charged particles all the way around. And this means you've got a strong strengthening of a dipole-dipole interaction. Of course, this could also be a hydrogen bond that's occurring between these as well. But in any case, you've got electrostatic attraction between the molecules within a particular substance. And if I just sort of close that in for a second, then we can possibly see what's going on. If I bring another molecule close, which also has a region of negative and positive charge, then we get this interaction. And if that interaction is strong enough to overcome these green forces over here, then you will have an interaction that occurs with, in this case, the water molecule. So our water molecule is now over here, and it's pulled one of the little solutes molecules with it. The key to that, of course, is that it wants to be surrounded. So we make sure that if we're drawing, say, a cation like sodium, then the water molecules are going to be orienting themselves around that sodium in such a way that the negative charge or the slightly negative region of the molecule is always attracting through these interactions between the negative and the positive charges. This is the electrostatic attraction, and this is the sort of thing that we're trying to look at when we're trying to represent how substances are dissolving in water. The same is true, of course, if we were to have a chlorine ion or any other part of a charged molecule, and we just need to make sure that we're showing how the parts of the water molecule, you can sort of continue them off wherever you want, really. But that these are now the positive parts of the molecule, and again, they're interacting with this negative charge. So surround them with water, identify the substance initially with some sort of generalized diagram showing a negative and a positive region and how the water molecules are getting in there and pulling these other ones apart. To sum it up, I guess, polar molecules are held together by polar bonds. The polarity of the water molecule interacts with the polarity, any type of polarity, positive and negative charges, slight positive and slight negative regions, and they pull them away until the water molecule surrounds the other individual ions or molecules. And this produces a nice pattern of particles where the solute is surrounded by the solvent molecules, and of course the solvent is always, for our purposes, going to be the water molecule. Have a bit of a play around with it. Make sure you can draw these, because it's very important that you're able to explain solubility with some simple diagrams that just help you to identify what's going on. And thanks for watching.